Now, we've done some things before with graphing quadratics, of course, graphing our parabolas. But now we get to add a little twist in, the inequality arrow. So now we're going to be doing some shading with some things. But there are some hints that we can take on that are going to make this a little bit easier. So, up at the top, there's 3 questions. We're going to give ourselves a couple of notes up here to help us out and make this easier. So number 1 says, should the function's boundary be solid or dashed? And that literally means the parabola itself. If your inequality arrow is or equal to, has the line underneath, we're going to use a solid parabola. If it's just greater than or less than, no or equal to, then we're going to use a dashed line to show that portion. Number 2 will get answered in some different ways as we work through these. Sometimes we may want to factor and find intercepts. Other times we may need to use the vertex formula, our negative b over 2a, to find our x and go that way. It varies. So that's going to change a little from section to section. But then where do we shade? Now, if you've ever done anything like this, you may have been taught to use a test point. Okay? I use that more in my regular Algebra 2 class because, well, it just seems easier for them that way. You guys, I think, though, can handle something that might work a little bit quicker for you. So, trying to figure out if I shade inside my parabola or outside, here's a general rule of thumb. If your parabola is opening up, if your a value is positive, if your y is greater than, you'll be shading inside the curve. So if it opens up and is greater than, we shade inside. And I am going to show you the test point as we go through here in case you're more comfortable with that. If my parabola opens down, if it's negative and my y value is less than, I'll shade inside the curve. I'll shade inside the parabola. So it depends on which way my parabola is opening. And then it's just the opposite for my outside. So if my parabola is opening up, in other words, if my a value is positive and y is less than, I would be outside the curve. And if it opens down and my y is greater than, it would be inside. You're like, okay. But again, I can also use a test point, which I'll talk about on a couple of these too, just as kind of a secondary plan, because I always like to have as many tools in the toolbox as I can. So when I get down here, it says, okay, graph each inequality. You'll notice on the first group up here in the top that they're all in standard form. Okay, they're not in vertex form, they're not in intercept form. So what I'm more than likely going to have to do in this first group is deal with good old negative b over 2a when it comes to finding my vertex's x value. So I take a peek and I go, okay, so my x is going to be the opposite of b, so the opposite of negative 8 is 8 over 2 times a. 2 times 1 is 2. So I find out my x value is 4. And then to find y, of course, we're just going to substitute that in. So y is just going to be 4 squared minus 8 times 4 plus 17. And yeah, I know it's an inequality, but I'm just finding the actual y value right now. That's why I don't have the inequality arrow in here. So that'd be 16 minus 32 is negative 16 plus 17 is 1. So my vertex would be at 4, 1. At this point, and that's just me, I would probably, if I had access, go to the calculator because it's always going to be easier, once I know what my vertex is, to get my other points by just using the chart. Because the nice thing is, I also then, as long as my vertex is in the middle, I get to reinforce I have the right answer because I see the symmetry that's involved. So in this case, let's see here. We got 5, 2, and 3, 2. We got 6, 5, 2, 5. And again, 5 points is enough. If you can fit in the other ones and you want to do that, you can. But again, be careful before you go flying along, because remember, we have some decisions to make on this one. First decision is, what type of line am I going to be using, or what type of boundary marking am I going to be using? Solid or dashed? Dashed, because it's just greater than. So I'll go dashed here. Now, here's where we'll talk about your options on figuring out where to shade. Since my parabola is opening upward, my a value is positive, and my y value is, my y is greater than, what's going to end up happening is, basically I'm telling you, you're going to shade inside of here. But if for some reason you're like, yeah, I'm not sure if I'm going to keep this straight, if I'm doing like a quiz or a test, trying to remember that for sure, here's your other option. If you wanted to run a test point, what I tell people is test a point inside the parabola. If it's true, you're going to shade inside the parabola. If it's false, you're going to shade outside. So like for instance, maybe I find a point that's inside, like 4, 3. Okay? Any point in there would work. So if I happened to test 4, 3, my x value is 4, my y value is 3, and I just plug them in. So I'd be like, okay, so 3 is greater than 4 squared is 16, minus 32 is negative 16, plus 17 is 1. Is 3 greater than 1? Yes. And if it's true, I shade where my test point is, which is inside the parabola. So that's always a backup plan if you're like, yeah, I might get those backwards, and that would be bad. Okay? So either one of those would work. So I start to notice, I'm like, okay, this one, yeah, I got to use my negative b over 2a again. So we're going to kind of get some practice here with our vertex form. And again, the details of what is what will get you here if you're not watching it. So again, negative b, negative 6 over 2 times a is negative 3. Again, plug that negative 3 in to get your y. Make sure you use parentheses if you're using the calculator. So I'd have 9 minus 18 would be negative 9, plus 4 would be negative 5. So here my vertex is negative 3, negative 5. And if you didn't have a calculator, again, a graphing one to kind of play with here, just a thought, you always could get a couple of points going here, and remembering that symmetry is involved. So for instance, if I plugged in negative 1, and some of you are like, okay, I've already got the chart up. I know. So it'd be negative 1 squared would be 1. 1 minus 6 is negative 5. Plus 4 would be negative 1, and the symmetry lets me know that would be the same value I'd get for negative 5. So I don't have to do this 4 times. If I do it with negative 2, negative 2 squared would be 4. 4 minus 12 is negative 8, plus 4 is negative 4. And if I had the calculator, I just used the chart for that. So either way, didn't even take me too terribly long of a time. Just doing it mentally. So let's see here. What do we know? Looks like solid, because we have the or equal to. So we'll get that drawn in. And then again, if I'm feeling comfortable enough with it, when it opens up, but y is less than, opens up, y is less than, what did I just do? Oh no, silly man, outside the curve. Because again, when y is less than, we're outside when it's up. When it's less than, we're opening inside. So everything bases on my arrow. So as you start to do more of these, you're like, okay, let's see. What if we went to 4? It's like, dang it, I was in the middle of 3. It's my one way to get caught up to you. So I come down to 4 and I notice a couple of things. I notice my a value is negative down, so I know it's going to open downward. So let's see, x is negative b over 2a, which is negative 2. Again, one of those detail things to watch for. So my x value of my vertex is 2. Then my y, and again, be careful here. Remember, this is negative 2 squared, not negative 2 squared, but the negative's outside here still. Plus 4 times 2 minus 6. So 2 squared is 4, then do the negative. So negative 4 plus 8 would be positive 4 minus 6 means my y value is negative 2. So my vertex is at 2, negative 2. And again, if I've got the calculator, the nice thing is I can double check and make sure I'm not doing anything silly. So let's see here. So negative x squared plus 4x minus 6. Let's see if I got my vertex right here. Looking good. See my symmetry. I'm like, okay, so 2, negative 2, 3, negative 3, and that's a good sign too. I see it's opening downward, so I'm not worried I put something in wrong. And then I just go through my little battery of questions. Okay, it's just less than, it's not or equal to. So go ahead and get that set. And again though, now remember, now we're opening downward. So we're downward and we're less than. And when we're downward and less than, we're inside the curve. But again, I could use a test point if I wasn't comfortable doing that. Maybe I test like 2, negative 5, something that's in the middle of my parabola, and then I can be sure if I need to be. Now there are some good things that can happen with these too. I can still just keep doing negative b over 2a. If you're a creature of habit and you like to do the same thing every time, that works out okay. But occasionally, you're going to have the opportunity to use a different format if you want to. For instance, here I look at this, and since the golden rule of factoring is always in my head, I remember, oh yeah, these have something in common. I can take a 2x out of here. So I could factor this if that's ever possible with any of these. I'd be like, okay. So I get that factored out. Well, now what? Well, now it's an intercept form. So I could take each of my factored pieces, set them equal to 0, and find my x-intercepts. So my x-intercepts would be at 0 and negative 2. And then if you remember back to when we were doing this earlier in the unit, it's like, oh yeah, now the vertex is going to be in the middle, and that's what I've got to find. So basically, I'm finding the midpoint of these two, which just would be at negative 1. So as far as my vertex goes, my x would be at negative 1, or I can always add those values together and divide them by 2. And then if I stick in negative 1 for x, I get 2 minus 4, which is negative 2. And once I have that third dot when I'm in vertex form, I'm good to go. I got me a really skinny graph here, which is going to have a solid line. But the rules would still apply like they did on all of the others. So for instance here, I see we're opening up where y is greater than, so we're going to be inside the curve. And we're good. So if it factors and you like doing the intercept form better, that's fine. If you wanna, every single time I see a squared and an x value, you wanna use negative b over 2a. That's fine. Either one of those will work and you'll be very successful. So okay, what else can we What else can we do with these? Well, we also can take the finished graph and write the inequality for it. So here's how this is going to work. What I need to know on these, first of all, is what my vertex is. So for instance here, my vertex is at 3, 0. I can visually see that. So when I think about vertex form for a parabola, remember that's going to look like this, where I can get my vertex from the HK. So when it says write the inequality for each graph in vertex form, all I'm going to do is plug in the values. X minus h squared. And I don't have to put in the plus 0. I would assume that. So I could just leave it this way. But since we're just asked to do it in vertex form, that would be it. If we were told to put it in standard form, we'd FOIL this out and then just combine any like terms that we had, and that would get me back to the solution, which I might actually do on the next one just to show anyway. And my apologies on where it says fixed scale. Oh, yes, I'm sorry.
Wouldn't you need to put like the correct is greater than or is equal to sign for it?
Oh my goodness. Yes. You're absolutely right. So two things, and you were correct in the first thing. Yeah, I kind of need an absolute value in here because if I don't have my inequality arrow, there's going to be no shading. So what am I going to want for my inequality arrow on this one? If I want to shade on the inside with a solid parabola. Greater than or equal to. Here I can say I was heading that way. I just forgot the other part of the arrow. Let me off easy that way. Because we're inside the curve and we're opening upward. So we'd want the greater than, and then we need the or equal to get the parabola. Thank you for that. Now next here where it says fixed scale, which as we can see I did not get situated, this 12 is supposed to be a 42. There's where my scale got kind of messed up. So we'll get that fixed up. So where does it look like my vertex is this time? Where's that vertex at? They're like, hang on, we are busy getting the answer while you are waiting. So negative 236 looks like where we're at as far as a vertex goes. So if we just want to get it into vertex form, one thing to be careful of this time, I'm going to leave my arrow B for a minute. What am I going to have to do? Because I know this part. What do I have to do to make the parabola open down? Yeah, I need a negative a value. So I need to have a negative in front of my quantity x plus 2. And since we're opening down, and I want to be inside the curve, what do I want to use for my inequality this time? Okay, yep, less than, and since it's solid, or equal to. That would be vertex form. And like I'd mentioned, if you're ever asked to go into standard form, you would just FOIL this out and then go ahead and combine like terms, and you'd be into standard form. So it's kind of a nice flexible way of being able to write these. All right. Any issues before we head to the back here? Yes, sir.
Are we going to have any things like that where the a value is greater than 1? Or like 1 or negative 1?
I have one on the assignment, and I'll tell you what you're going to want to do to think about that a little bit. When you're looking at those, you're going to want to take your vertex value and one of your values that's down further, and there'll always be multiple points on any of the problems that I give you, and basically you're going to treat it almost like you would treat a slope type problem, where you're going to look and you're going to say, okay, what's my quote unquote rise over run, so you can kind of see how that stretch works. But if that's one we get stuck on, that's one we can talk about more too with that. But that's a very good question. Because, yeah, I needed to get one of those in here is what would have been nicer. But these are both just typical standard ones. Other issues before we flip on over? Not yet. All right. To the back we go. All right. So solving quadratics in one variable. Now, when we get to these, we can do it graphically, like we have been, using intercepts, or we can do it algebraically. And again, it's sort of one of those optional things. So when we get into a situation like this where my y value is gone, typically with these now we're going to be able to factor them and use intercepts. So let's see here. Multiply to 5 and add to negative 6. All right, x minus 5, x minus 1. So here, to get my intercepts again, I'd set each quantity equal to 0. So my intercepts are going to be at 5 and at 1. So I've got 2 of my points. Now again, to find the vertex, I want to find the midpoint of those. Now in this case, again, I can kind of count and see that. But again, normally I can take those two values and divide by 2 to get my x. But again, don't just put a dot at 3 then, because that's not where my vertex is. I still need to know what the y value would be. Like, but I don't see a y anywhere. To get the y, I'm still going to plug my values in here for x and figure out what this side of the expression would be. So for instance, here I'd have 3 squared minus 6 times 3 plus 5, or I could go to the calculator if I wanted to, since I know the x value. And my y is going to end up being negative 4. So my vertex is at 3, negative 4. So I'm like, okay, looks like it's opening up. That's a good sign because my a value is positive. I don't have the or equal to, so I'm going to go dashed here. Now you're like, okay. Now you'd always talked before about how if it was y whatever, that's how I figured out where I was going to shade. I don't have a y here anymore. Treat the 0 as though it were the y. So this would still be y is greater than, because we're looking at it from the 0's point of view here. So let's see here. Opening up, and we're at y is greater than. Up, y is greater than, we're inside the curve. And again, if that's one of those, especially if we're doing the y and you're not sure, find some easy point that's inside the parabola, like 3, 0 would be, and simply test that out. You're like, but wait a minute, there's nowhere to plug the 0. There's no y. That's true. But I could still plug in the x's in these places. And so if I were to plug that in, so I'd have 9 minus 18 is negative 9 plus 5 is negative 4 less than 0. Well, yeah. And again, that would reinforce that I shaded in the right place. But you'll also notice something else new here. It says interval. You're like, interval? What? How are we going to do interval notation with this? Basically, here's how it works. If you have a graph and you've shaded inside, your interval notation is going to take on the same characteristics as an AND statement. If you remember back to when we were doing AND and ORs with inequalities, AND statements are the ones that would come in and they'd kind of butt heads in the middle, and ORs would go out. So my AND statement basically is going to say, I want the values between these two x-intercepts. That's what I'm looking for. So my interval notation would just go from my furthest x-intercept, oops, bad boy, parenthesis, left, x-intercept 1, to my right, x-intercept 5. And I'm just looking for those values. So whenever we're inside, we're and. If we're outside, we're or, because, well, they start heading off in both directions. And we're going to see that on the next one as well. And that'll be true when we're doing it algebraically as well. So then I look and I'm like, okay, so these guys are always going to factor. Yes. And they'll be simple enough ones it's not going to rack your brains a whole lot. Oh, let's see here. -3 and 1, I think. -6, +1, yes. Set those equal to 0. Set that equal to 0, it'd get me 3. Those are going to be my intercepts. And the more realistic thing about this one is you're going to get values sometimes that don't come out pretty. And that's okay. Because like here, I can't really count to the middle. So when I go to find my vertex, I'm going to do -1/2 plus 3 divided by 2. And again, if you're going to the calculator, use the parentheses up in your numerator. So 2.5 divided by 2, yuck. 1.25. Lovely. Because that's going to be even more fun to plug into the calculator, which is what I'm even going to do. All right, let's get out of here. So we want 2 times 1.25 squared minus 5 times 1.25 minus 3. Okay. And yes, you can get some ugly stuff. So basically, -6 and 1/8. So my vertex is just past 1 and just under -6. And again, the nice thing about intercept form like this, I only need the 3 points. So I get those. I notice it's going to be a solid. And then again, remember, we're looking at it from the zeros point of view. We're looking at it like it's a y. So this time, my y is less than. When y is less than and we're opening up, that's going to be outside. And again, when we do the outside on these, my interval notation takes on the characteristics of an or statement. And again, or goes out. So when I think about that for a minute, basically what I'm looking at here would be the equivalent of this going here and going out and that going out, if I wanted to look at it that way. So I start way out here because the shading goes even beyond my graph and keeps going forever to -infinity. And then as I start coming up, there's my first stoppage point at -1/2 with a bracket because it's or equal to. And then there's a little blank space in here. Oh, here I start up again at 3 and head off forever to +infinity. Oh, double question.
What if there is no x-intercept in the...
With these, you would end up with something that actually become a no solution. Yeah. If you have one of those, you'll have a no solution. There's even one that comes up where you may get like a single x-intercept. That's going to be a different issue. But we're going to come up on that one here in a minute, too.
For x, shouldn't it have been 2.5 divided by 4? Because it's 2 times a is 2.
Okay, I'm not using the actual vertex form on that, the -b/2a. What I'm doing here is, when I have 2 intercepts, what I'm doing is for the x values, I'm trying to find the midpoint of those. So this is more of a midpoint formula that I'm using here instead. Now, could you have, if you wanted to, back with the original problem, done -b/2a and gotten to your vertex that way? That absolutely would work still, and it would be 4 then. Good questions. Any other ones? So we got one last little part here to play with. All right. So let's see here. Algebraically, find the zeros of the function, then test the values on a number line. Okay, all factoring all the time. So let's see. Multiply to -8 and add to -2 would be -4 and 2. And we're still going to set those equal to 0 to find the zeros. So basically, we're just switching signs here. And those are my intercepts. You're like, okay, but now it's a number line. So how exactly does this work? Here's how it's going to work. We're going to get my two values on here. Basically, now these are going to start looking like ones that we did before. What's going to happen is either you're going to find a true value that works in this area, or you're going to find one that works out. And there's even a shortcut to this, but I'm going to save that for a second. But it's always going to be one or the other. It's either going to be shade in the middle or shade on the outside. It typically, except for the rare exception, will not be both. So here's what I normally do. I normally figure out wherever the 0 is going to fall, and that's what I test. So here 0 happens to fall in the middle. So let's test out 0. 0 minus 0 minus 8. So is -8 greater than 0? No. False. So since it's false in the middle, that means it's going to typically be those outer areas. Here's the other reason that I know that. Notice in my original inequality that this value is greater than 0. When we used to graph these before, greater than was typical of an OR statement. And OR statements go out anyway. So I can kind of cheat on this even and say, oh, if it's greater than, it's OR, and it's typically going to go out. And I know how to graph these. I just do negative infinity up to my point, remembering in this case, since it's not or equal to, that these are going to be parentheses. Closes off, because I have a gap here in the middle, and starts up again afterwards. So can I test a point? Sure. Probably a wise idea to do, even though this kind of gives me an idea of what's going to be going on. And that's going to be true for any of these that I'm doing algebraically. Like, I don't want to cheat every time, because about the time I cheat every time, I'm going to get to an exception. I'm going to get burned. But like here, I see it's less than. Pretty sure this is going to be like an and statement. It's probably going to come in the middle. I'm going to make sure, though. So I'm going to set these guys equal to 0. Again, those are my intercepts, or my zeros, of course. Now again, this is just me. If you wanted to test like -1 to test the middle, you could. I like to keep testing wherever 0 would be. So again, that makes life simple. 0 plus 0 plus 2 is 2 less than or equal to 0? No. Which typically then tells me it's going to be this middle section with brackets. And the nice thing about that is basically it's just your two endpoints. Now, are there going to be some weird ones? Because every time we think we got this down and have touched every possibility, we find something that does goes wacky. So, I want to show you a couple of weird instances that could pop up. And here's one of them. What happens if I factor and I get the same value? I only have one x-intercept. How's this going to work? Make a number line. Let me think about this for a minute. So 9. There's no places to guess. There's nothing to look at. I mean, how's this going to... Here's what you have to think about. If I were to test a point on each side, like 8 and 10, let's say. If I plug in 8, 64 minus 144 is negative 80. Plus 81 would be 1. Is 1 less than or equal to 0? No. So this side doesn't work. But then it gets fun. Let's plug in 10. 10 squared is 100. That's 180. 100 minus 180 is negative 80. Plus 81 is, 1. That doesn't work either. But 9 works. Okay. 9's the only number that works. It's the only solution. Ew. That's kind of brutal. And that's actually just the start of the fun. If I try to factor, here's another instance that can get me into trouble. I go ahead and I take out what they have in common and I try to factor what's left. Well, it doesn't factor. Do I just get to say I'm done? There's nothing I can do? No. Got to use the quadratic formula then. Ew. Some of you still got to work on getting that up here too, so this will give you a chance to do that. So again, it's negative b, and it's just what I'm working with in here, plus or minus the square root of b squared minus 4 times a times c all over 2a. Ooh, I have a different problem. 8, that's 40. 36 minus 40 is negative 4. Wait a minute. If I can't graph this, I'm going to get an I. You're right. There's no real solutions to this. And that kind of goes along with the question that was asked earlier. What happens if I graph it and there's no x-intercepts? This would be an example of one of those. And if you get one where you test it and everything works, you're like, everything works? Oh yeah, this can happen. Here's the one other thing I did want to make mention of and why I want to do 15, even though I want given time, but I wanted to show how this works. If you don't like factoring with a negative, there's a way around this. And basically what you're going to do is, you're going to divide all the way through here by negative 1. Now watch what that does though. If I divide through by negative 1, which is perfectly legal to do, yeah, when you divide by a negative, you've got to remember to flip the inequality arrow if you're going to do that. Perfectly legal, though. Because now you're looking like, well, I can factor this. At least I think I can. Let's see. Or do I have to go to the quadratic? Let's look. Oh, I think we're going to the quadratic. Okay. We're not doing that. So negative b of b squared 4ac. Oh, I think we're going to go back into negative land again. Did I do something goofy? But is that going to give me positive 15? Because remember, this sign switched too. If I did negative 5 and positive 3 or negative 3 and positive 5, this would have to be minus 15, and I had to switch all the signs with that. But I did the same thing the first time I did this. So 4ac, oh, I'm going to end up in the same problem again. All over 2a. Yeah, I'm going to end up with an imaginary again. Okay, so I'm no real again. But just in case sometime if you are trying to factor and you hate dealing with that negative, that's what I wanted you to see, that you've got that option. Whew! That's some crazy stuff. Some crazy stuff. Get you some play in there on that other sheet that you picked up, the section 5-8. And I do promise that